Hey everyone. Okay, so we're going to build off of what we were talking about last time with what we can learn about stars, the physical properties of stars, and then we're going to build on there to say, well, what else can we figure out? Based on what we know, what more can we learn? All right. And that has to do partially with what you can determine about a star from its position on the HR diagram. Which hopefully you've looked at the homework and have already seen. But we'll get into that. So, quick recap, right? There are three basic things. There are three basic measurements that you can get directly from a star. Apparent magnitude is how bright a star looks, right? You look at a star, how bright does it look? That's the apparent magnitude. If you watch it and observe the parallax of the star, then you can take that parallax angle and figure out distance. And then if you've got apparent magnitude and distance, you can figure out absolute magnitude, and from absolute magnitude you can get luminosity. The third thing besides apparent magnitude and parallax that you can measure directly from a star is the peak wavelength in the spectrum, right? You take the light from the star, you break the light up into the spectrum, you say, well, what wavelength is the star brightest at? That's the peak wavelength. And the peak wavelength tells you the star's temperature. So now we know a second thing, or a second real physical thing about a star. We know how hot it is, how hot the surface is. And that is, let me emphasize, that is the temperature we're measuring here. Right? When you take the peak wavelength in the spectrum and determine the temperature, it's the temperature of the surface of the star because that's where the light is coming out of. Right? That's the light that we see is coming off the surface. Okay. Now the technology to measure parallax and peak wavelength well really was getting good in the late 1800s, early 1900s. And so you had people doing this en masse. You had people making large catalogs of magnitudes, luminosities, distances, parallax, and temperature. And when these people, started comparing notes to say, well, you've got the luminosity of all these stars, I've got the temperature. Pardon me, a hiccup there. Let's put our heads together. What else can we figure out? They started constructing the Hertzsprung-Russell diagram, or the HR diagram. And on the face of it, the HR diagram it's just a scatter plot of luminosity versus temperature of these stars, right? And an HR diagram is always set up the same way. You have the luminosity on the vertical axis, and you have the temperature on the horizontal axis, right? So luminosity on the vertical axis, where you got the bright stars on the top and the faint stars on the bottom, hopefully pretty straightforward. The temperature is always on the horizontal axis, ranked from hot to cold. So it's a little bit backwards there. So the hottest, bluest stars, right? Because remember, hot means blue. So the hottest, bluest stars are on the left side, going down cooler, cooler, cooler until you get the coolest, reddest stars on the right side. Okay? If you take any random patch of sky and you look at all the stars in that patch of sky and you calculate the luminosities and the temperatures and you plot the stars on this graph, this is pretty much what it always looks like. What you'll notice is that these stars are not scattered all over this graph. Stars don't happen in any random combination of luminosity and temperature. And that should be a huge red flag? That should be a huge flag that tells you something's up here, right? You always find stars, most stars. There are always the weird exceptions, but, by and large, you always find the stars along this diagonal line, which is called the main sequence, or in a cluster over here, a cluster here, and a cluster there. That's pretty much it. You don't find very many stars in this black area here, these black areas over here. Stars clump up into these 4 groups. That's telling you something, right? Something about the way stars work means that you find them in these 4 groups and not anywhere else. What's going on here? Well, let's see if we can figure this out. Pardon me. Okay. Another annotation here is that when the temperatures of stars were being measured in large groups, again around the early 1900s, they had to find a way to organize the catalog because they were getting the spectra and measuring the temperatures of thousands of stars every night to make a giant catalog of lots and lots of stars and get their temperatures measured. So at some point they had to figure out, like, well, we've got so many thousands of stars, we need a way to organize our file cabinet. And so initially they just started calling stars like, okay, we'll call these ones A type, B type, C type, D type, et cetera, et cetera, et cetera. And then a few years later, they realized, like, oh, wouldn't this be easier if we just, instead of organizing them somewhat arbitrarily, why don't we just catalog these stars? Why don't we rank these stars from hottest to coldest? Which is why the HR diagram is ranked from hottest to coldest, bluest to reddest. And so they went to the file cabinets and they said, oh, okay, well, which stars are the hottest stars? Well, it turns out the hottest stars in the universe are what they had already been calling O-type stars. So they just took all the O-type stars out of the catalog, out of the file cabinets, and put them first. And then they're like, all right, so the second brightest, so not the brightest, the second hottest stars are what they had been calling B-type. And then, so the O-type and the B-type stars are the hottest, the bluest stars, like you can see here, right? Hottest and bluest. A little cooler than that, but still pretty darn hot, are the A-type and the F-type stars, which are whitish. Cooler than that are what they had been calling the G-type stars. So G-type stars are yellowish stars, so our sun is a G-type star. Cooler than that are the K-type stars, which are more orange. And then the coolest stars are the M-type stars. So the M-type stars are the coolest and the reddest. And then when they started doing this, they also just combined a bunch of letters into one. So this is why they didn't use all of the letters of the alphabet. They ended up taking several letters and just saying, like, oh, okay, B, C, and D, we'll just lump B type, C type, and D type, and we'll just lump those all together into B. I think that's true, but you get the idea. Like they ended up consolidating the alphabet so that once they were all done, the alphabet of spectral types ranks the stars by this sequence of letters. O, B, A, F, G, K, M. O are the hottest and the bluest. M type are the coolest and the reddest. So this letter, there's a lot of information packed in here, right? So we're going to use this. We're going to use these letters throughout the rest of the semester because this is kind of a handy shortcut. If I say, oh, that's a B-type star, that one letter tells you temperature and it tells you color. Right? B-type means, oh, okay, it's hot. How hot? Well, B-type stars are around, 20,000 Kelvin, and they're bluish white. Right? So that tells you a lot. Notice the spectral type, that letter, the spectral type does not tell you luminosity, because you can have a B-type star that's faint down here, or you can have a B-type star that's here or here. So you can have stars that have very different luminosities, but they're all the same spectral type because they're the same temperature and color. Okay? So it would behoove you to remember that order of letters, O, B, A, F, G, K, M. what else can we figure out besides just looking at this graph and looking at luminosity and temperature? Well, like we talked about in the previous lecture, the luminosity of a star depends on the temperature and the radius of the star. So if you already know the luminosity and the temperature, you can look at the radius. Now, what I was telling you in the last lecture about how you can take this equation and you can take this equation, or you can take the simplified one that I gave you. And you can do the math if you have to, which is, if you want to do the calculation and if you want to figure out what the radius of this star really is, then sure, do the math. You've got your spreadsheet already set up, so it'll do the math for you, fine. Sometimes you don't have to, though. Sometimes you can just eyeball the HR diagram and it'll give you a sense of what the radius of the star is. Right? Some stars have a high luminosity because they're big. Some stars have a high luminosity because they're hot. Some stars have a high luminosity because they're both. But since you've got this graph of luminosity and temperature, you can just eyeball the graph to get a sense of, is this a big star? Is it a medium star? Or is it a small star? For example, what do you think? Oop, go on. There you go. On the HR diagram, where are the largest stars? Where would you find the biggest stars? Which corner? Well, if the star is big, then you'd expect it to be bright, high luminosity, because luminosity is proportional to the radius squared. So you could think like, oh, it must be A or B. Right? Now, the A or B, right? These stars must be big because they're bright. Okay, but stars at A and stars at B have different temperatures. So which is it? Is it A or is it B? Which star is going to be bigger? Well, what do we know about stars at A? They're bright and they're hot. So where does the luminosity of a star at A come from? If a star is at A, is it getting its luminosity from its temperature or from its size? Well, you know that the star is really hot, so it's probably getting its luminosity from its size. These stars at A don't have to be that big. They don't have to be as big because they can get their luminosity from their temperature. What do we know about stars at B? They're bright, but they're cool. How can you have a star that is this bright? What is this? 100,000, a million solar luminosities. Stars up here have a million. They're a million times the brightness of the sun, and yet they're not very hot. How can these stars be this bright when they're cool? They must be getting their luminosity from their size. They must be getting their luminosity from their radius. These stars must be really, really big because they're certainly not getting their luminosity from their temperature. Right? So yeah, the stars at B, those are going to be the biggest stars. What about this? Where would you find the smallest stars on the HR diagram? It's C, right? Stars at C have the opposite problem. These stars are really faint even though they're hot. How can a star this hot and this blue be so faint? It's because they must be really, really small. Right? These stars in the corner at C are so tiny that they don't have very much surface area and they can't let the light out. And since the light can't get out, the stars can't be very luminous. So you can just eyeball the HR diagram and get a sense of what the radius of the star would be. Small stars over here, going up to big stars over here. So as you go diagonally from lower left to upper right, the stars are getting bigger and bigger and bigger. That's why these stars down here are called white dwarfs. They're white because they're hot. They're white hot, or some of them are blue hot. And yet they are so small that they have temperatures significantly, sorry, they have really hot temperatures, but they have luminosities significantly dimmer than the sun, even though they're much hotter than the sun, because that's how small they are. How big is a white dwarf? A white dwarf is about the size of the Earth. That's really small for a star. And that's why these stars up here are called supergiants, because these stars are supergiant. They're so big, they have to be this big because they've got these super high luminosities, even though they're really cool. How big is a supergiant? These stars up here are more than an AU in radius. Meaning, if you took a red supergiant and plopped it down into the middle of our solar system, the Earth's orbit would be inside the star. So yeah, supergiant. All right, so this HR diagram is great for eyeballing. Just look at the graph and you can look at a star and say, here's what its luminosity, here's its temperature, and here's its radius, without having to do much math. Well, that's nice. Like I was saying a minute ago, right? You find almost all the stars in the galaxy in these 4 groups. Most of the stars, though, about 90% of the stars in the sky fall along this diagonal line here, what's called the main sequence. This diagonal line is called the main sequence because this is the main way that stars happen. 90% of the stars are on the main sequence. The other 10% are giants, supergiants, or white dwarfs. So let's look in more detail at the main sequence because this is the way most stars happen. One of the things that you can't tell just by looking at the HR diagram is the mass of a star. At least not directly. But over a few decades, they studied binary stars, binary main sequence stars. So what is a binary star? A binary star is 2 stars that are orbiting around each other, 2 stars that are gravitationally bound to each other, the way that the Earth is gravitationally bound orbiting around the sun. And so by studying 2 stars as they orbit around each other, you can measure what the mass of the stars are. What the mass of both stars individually are. You are going to get some practice on this in a few homework assignments, so you'll see this in practice shortly. But for the moment, I guess take my word for it for just a minute, for a little bit until you do the homework and can see this in practice. But the awesome thing is that when you study those binaries and you get the mass, and then you say, well, we know what the luminosity is because we have the distance, so we can get the luminosity. And you measure the mass from studying the binaries. When you take a whole bunch of main sequence stars and you measure their luminosities and you measure their masses, if you graph luminosity versus mass, those 2 quantities are a nice, tight, straight line. Luminosity and mass are absolutely related to each other, and that's not a coincidence. The higher the luminosity of the star, the higher the mass of the star. Why? The luminosity, these stars are higher luminosity because they're higher mass. It turns out that the mass of a star, especially a main sequence star, the mass of a main sequence star determines what its luminosity is going to be. These stars down here are low luminosity because they're low mass. These stars are high luminosity because they're high mass. The mass that a star is born with determines what its luminosity is going to be when it's on the main sequence. Let me underscore this. This relationship is true. This straight line only works for main sequence stars. It turns out, for reasons we're going to get into in a day or two, main sequence stars are very well-behaved stars. Main sequence stars are very stable, very well-behaved. They control themselves very well. They are a well-behaved child. Sort of. Maybe this metaphor might work. We'll find out. So that the relationship between the luminosity and mass is that luminosity is proportional to the mass to the 3.5 power. That's the equation for this trend line. Which means if we take this equation and rearrange it, the mass of these main sequence stars is proportional to the luminosity to the 1 over 3.5 power. So, and this equation, by the way, is in solar units. So solar mass, the mass of the star in solar masses, equals the luminosity in solar luminosities to the 1 over 3.5 power. Now, I said a minute ago, you can't just look at a star and know what its mass is. Unless you know that it's a main sequence star. Because it sure looks like, for all main sequence stars, they lie along this straight line where the luminosity and the mass are related to each other like this. So, if you discover a star, let's say you discover a brand new star. No one's ever seen it before. Nobody knows anything about it. You can still figure things out. If you take this brand new star you just discovered, you measure its luminosity, you measure its temperature, and you say, well, where does this star land on the HR diagram? If you know that this is a main sequence star, and again, this relationship only works for main sequence stars. Now, luckily, main sequence stars are 90% of the stars, so this is super powerful. But I just want to give you this, take this with a grain of salt. This relationship only works for main sequence stars. Okay? But if you look at a star, and if you measure the luminosity and the temperature, and you say, well, that lies along this line, that's a main sequence star. If you know that's a main sequence star, you can use that equation to figure out what the mass is. Turns out, the mass of the star is the most important thing to know about it. Let me say this again. The mass of the star is the most important thing to know about it. Because if you know what the mass is, you know what its luminosity is going to be. And the mass and the luminosity determines where the star lies on the main sequence. Right? The highest mass stars are all up here on the top of the main sequence. These stars are bright. These stars are hot and blue. These stars are big. Why? Because they're high mass. The mass of a star controls everything. The mass of a star is its destiny. Every star that is 30 solar masses, like it says here on the graph, every star that is 30 solar masses will have this luminosity, this temperature, this radius. The mass that a star is born with determines everything else about it, including where it's going to lie on the main sequence. And so as you go, the highest mass, hottest, bluest, brightest stars are up here, and as you go down the main sequence, the stars get cooler, dimmer, smaller, redder. Why? Because they're getting lower mass. Because the mass gets smaller and smaller and smaller, so here you go. 6 solar masses, 3 solar masses, 1 solar mass, 1/10 of a solar mass. As you get to the bottom of the main sequence here, these stars are small, they're dim, they're cool, they're red. Why? Because they're low mass. I skipped over this real fast here, didn't I? So, to double back here. There's one thing that all main sequence stars have in common, though, right? As you look across the main sequence, these stars are all different colors, different luminosities, different radii, different masses. There's so much that is different about all of these stars. The one thing main sequence stars have in common, the one thing that makes them main sequence stars, is their power source. Every main sequence star is powered by hydrogen fuel. Deep down in the core of these stars, hydrogen is fusing and transforming into helium, and that releases the energy that keeps the star shining for as long as there's fuel to burn. Right? That's the definition of a main sequence star, a star that is powered by hydrogen burning, hydrogen fusion in the core of the star. All right? And stars spend 90% of their lifetimes burning hydrogen to power themselves. And since stars spend 90% of their lifetimes fusing hydrogen, that's why 90% of the stars in the sky are main sequence stars. Okay? So I said, oh, you can't just look at a star and figure out its mass. You can't just look at a star and know its mass. Unless it's a main sequence star. And then you can use the luminosity, right? You know the luminosity from the absolute magnitude. If you know the luminosity of a main sequence star, boom, you've got the mass. And if you know the mass, you know everything. Because the mass of a star is its destiny, including how long it lives. Because stars will eventually run out of fuel. What did I say a second ago? A star will live on the main sequence. A star will be a main sequence star as long as there is fuel to power it, as long as there is hydrogen fuel to power it. Eventually, the hydrogen runs out. How much time does that take? Well, the lifetime of a star is just how much fuel it has divided by how fast it's burning that fuel, divided by the rate at which it is burning that fuel. Think about it like this. Let me give you an example, right? You're on a road trip. You have 10 gallons of gas in your car, and you're going to drive down the highway, and you know that as you're driving down the highway, you burn that gas at 2 gallons per hour. All right? You've got 10 gallons of gas. You're burning the gas at 2 gallons per hour. How much time until you run out of fuel? 5 hours. Right? We're doing the exact same thing here. We're saying how much hydrogen fuel does the star have divided by the rate at which it is burning that fuel. Well, how much fuel the star has is proportional to the mass. Right? The higher the mass of the star, the more hydrogen fuel it has to burn. Pardon me. No. There we go. How fast the star is burning the fuel depends on the luminosity. Right? If the star is brighter, how is it giving off more energy per second? If that star is a higher luminosity, it's able to give off more energy per second because it's burning the fuel that much faster. Right? A star has to burn fuel fast enough to maintain that luminosity in order to give off that much energy per second. But we know for main sequence stars that the luminosity is proportional to the mass to the 3.5 power. So, what have we done here? The mass of the star is the mass of the star. The luminosity is mass to the 3.5. So, you can cancel out. 1 power of mass on top divided by 3.5 powers of mass on the bottom means that the lifetime of the star is proportional to the mass to the negative 2.5 power. Ignore the negative 2.5 for a second. Just realize the lifetime of a star, how much time that star will live as a main sequence star, is proportional to the mass to a negative power. Which means as the mass goes up, what happens? As the mass goes up, the lifetime goes down. The more massive a star is, the shorter it lives, the shorter a lifetime it lives. Okay? So that these stars up here, these 60, 30, 20 solar masses, these stars up here, these are high mass, they're really hot, they're really bright. How do you get stars that are this bright? They have to burn this fuel that much faster. Let's take the example on the previous slide here. We'll go back to that slide. Let's take a 10 solar mass star. Right? A 10 solar mass star has 10 to the 4 solar luminosities. So if you take a star that is 10 solar masses, it has to burn its fuel 10,000 times faster than the sun It's got 10 times as much fuel as the sun has, but it's got to burn that fuel 10,000 times faster in order to maintain a luminosity of 10,000 solar luminosities. So when you take the mass divided by the luminosity, 10 divided by 10,000 is 1/1000th, right? Being born, a star that is born with 10 times the mass of the sun is only going to live a lifetime that is 1/1000th the mass of the sun. Sorry, 1/1000th the lifetime of the sun. So these high mass main sequence stars, they live fast and die young, right? They burn their candle at both ends. These stars may be high mass, they've got more fuel, but they've got to burn their fuel so much faster to maintain that high heat, the high luminosity. They burn their fuel so fast that these stars are born, they live their entire lifetimes, and they die in just a few million years. That's it, just a few million years. There have been high-mass stars that have been born, lived, and died in less time than it's been since the dinosaurs went extinct. They don't live for very long. But as you go down the main sequence, these stars are getting less and less massive, which means they don't have to burn their fuel as fast. They're not as luminous. And since they don't have to burn their fuel as fast, they make that fuel last longer, so that a star like the sun is going to live a lifetime of about 10 to the 10 years. What is 10 to the 10? 10 to the 10 is 10 billion years. Right? Our sun is going to live a total lifetime of 10 billion years. And we know from geology that the Earth is 4.5 billion years old. So if the Earth and the whole solar system is 4.5 billion years old, so we're right about at middle age, right? The sun, the Earth, our solar system is right about at middle age. The sun is halfway through its lifetime, and the sun is going to live another 5 billion years before it runs out of hydrogen fuel in the core. These stars down here, though, they really last a long time. Right? These stars at the tail end of the main sequence, they're not very impressive, right? These M dwarfs, these red dwarfs, are small, they're cool, they're dim, they're red. No one's impressed by a red dwarf. But because they're so small, they don't have to burn their fuel very fast. So they can make that fuel last for hundreds of billions, maybe even 1 trillion years. Right? These are going to be the last stars left at the end of the universe. Right? At the end of the universe, 1 trillion years from now, all the high mass stars will be dead. All the medium mass stars like the sun will be dead. 1 trillion years from now, these little red dwarfs will be the last stars burning out the last of their fuel in an otherwise dark universe. That got really negative there at the end. So sorry about that. But that's what I mean when I say the mass of a star is its destiny. When a star is born, it's born with a certain amount of stuff. It's born with a certain amount of mass. It's born with a certain amount of gas. And how much mass that star is born with determines its color, its radius, its temperature, its luminosity, and how long it'll last until it finally dies. When a star runs out of hydrogen in the core, then it starts evolving and turning into the other 3 types of stars. So that's where the giants, the red giants, and the red giants, the red supergiants, and the white dwarfs come from, is that stars spend the first 90% of their lifetimes burning hydrogen, living on the main sequence. When they reach the end of their lives, when they start running out of hydrogen fuel, then they start transforming and turning into giants, supergiants, and white dwarfs. So that's why only 10% of the stars are those 3 types, because stars only live as those stars. Stars only live as those 3 types the last 10% of their lifetimes. All right. How do they evolve? How do these stars transform into other types of stars as they die? Is a way cooler story, and it is a really interesting story that we will get into in a couple of days. So, main sequence stars, right? Main sequence stars are nice, stable, well behaved stars. But when they start dying, then things get really interesting and a little complicated, and they really transform into other types of stars, which is I don't know. I nerd out about it. It's very cool, and so we'll get there in a couple days. Um, okay, just some questions to get you a little practice. All right, which of these main sequence stars, which of these main sequence types of stars is the most luminous? Which ones are the brightest? The A, the B, the K, or the M types? It's the B types, right? Why are B type stars the most luminous? Because B, out of those four, A, B, K, or M, out of those four, the B types are the hottest. And because the main sequence is a nice, well-constrained diagonal line, the hotter the main sequence star, the brighter, the higher luminosity must be B type. Consider these three stars. Which of these stars has the hottest surface temperature? Well, what of the information you're given, of that information that you're given, what information will tell you temperature? The letter, the spectral type, will tell you the temperature. So which of those is the hotter surface temperature, G, B, or K? B is. B is the hotter, bluer spectral type. So which one is the hottest surface temperature? Trillion is. Good. Which star's color is closest to the sun? What type of star, what color, what temperature, what spectral type is the sun? Our sun's a G-type. So what Ford is the G-type star. So Ford it is. Which of these three stars is closest to the sun? Sorry, well, closest to the Earth, closest to the sun, same thing. Yeah, that we don't know. Yeah, it's D. We don't have that information, right? The HR diagram is great. Why did I ask this question? Because I want to make the point that the HR diagram is great. The HR diagram tells you a lot about the star. HR diagram can tell you luminosity, temperature, radius, mass, all that good stuff. One of the things you might want to know about a star that you can't just read off an HR diagram is distance. So yeah, we can't get the distance to the stars using just that information. Okay. Go ahead and get a little bit more practice with this. Go ahead and open up the green book to page 117 and work on the HR diagrams tutorial just to get a little more practice with how we read these things, because let me not understate this. HR diagrams are a super useful tool for figuring out what's going on with stars. And so we're going to be looking at these for most of the rest of the semester. So I want you guys to get plenty of practice with how you read information out off of these diagrams. Because they are a way. They're a great shortcut for not having to get bogged down in the math, which, if you can do it, do it. So, all right. Go ahead, get that tutorial done, get that turned into me when you can. There will be some more tool belts for the lab posted also, so get those done to get that practice, and have a good one, everybody. Bye.